Blair resides in Mount Vernon, Iowa. He received his BSc with a geology minor and MSc in geotechnical engineering with a geology emphasis from Iowa State University. Mr. Blair is a licensed professional engineer in multiple states, including Texas. He has over 30 years professional experience projects throughout the United States and Canada. For the past 24 years, he has specialized in reductive delivery of infrastructure projects, including bridges, highways, airfields, slope stabilization, geohazard mitigation, and retaining structures. In addition to his professional design build experience, for 2 years, he taught geotechnical and foundation engineering as an adjunct instructor at the University of Texas, Tyler. After spending 15 years living and working around the U.S., he returned to Iowa in 2013 to continue his professional practice and finish raising his family. Mr. Blair remains active in civic, professional, and religious organizations. He has been married for over 30 years to I'll let you pronounce
Shereen.
And is the fellow to 4 doctors. Welcome.
Thank you. I'm really happy to be here. It was a bit of a journey with all that's going on with flights to be able to get here, but I found a flight this morning out of Des Moines, and so I made it. So I'm very glad to be here. Because this is a topic that is very near and dear to my heart. As Shingy mentioned, I've been in the profession a while. My first projects for transportation were metric jobs, and so that kind of dates me. And I've seen the implementation, the discussion this morning of LRSD and transportation projects with varying success, but in all, it all comes down to the engineer judgment. What I want to talk today, particularly, there's a lot of very experienced people here in this room, just looking at the hair, and particularly how we can help communicate this to the rising generation of engineers. I messed something up here. Oh, okay. All right, so this is my introduction. AI, everyone loves it. And geotechnical software really advanced, particularly in the past 5 or 10 years. And there's relatively low barrier to getting into. It's very easy to get into a software platform, open up, run the program, and have an answer. As a result, the ease of this application it's really huge. And we need more engineering judgment now than we ever did before. So we're familiar with artificial intelligence. There are distinct groups that are really pushing that artificial intelligence should be used everywhere and for everything. But artificial intelligence, I'm not going to read the whole slide. It's just, how many of you, what is your local practice for determining underdrain shear strength using an STP bore count? Just for that, the rule of, was it the Terzaghi 125 pounds per cubic pound per square foot per blow? There's other methods that correct for plasticity. Oh no, they're just empirical. They're based on a set of data, and as a result, we come in with a formula that we use over and over and over again. It's based on a set of data in which that empirical model was developed, and that is what AI is. AI simply is using big chunks of data to develop algorithms that can create answers based on that data. So the quality, breadth, and depth of the data set directs the creation and therefore the results produced by the model. So if you're dealing with a data set that's the internet wide, wow, it seems like that model knows a lot of things. But they don't possess judgment. And the other problem with AI, the thing you really have to help the rising generation understand, is they will always give an answer. Even if at first it's, well, I can't really say, well, what would you do? You ask the question again, they'll happily give you an answer, whether or not that answer makes sense. So this was a recent study. I'm sorry for the size of the font, but this recent study done by Deutsche Welle, BBC, and NPR about the accuracy of these large language models when they ask them questions about current events. And it is tremendously bad. So axis on the left, the y-axis is 100% error. Axis on the it's just a bar graph. They did Copilot, ChatGPT, Perplexity, and Gemini, four large language models. Gemini had 78% serious errors when asking questions about current events, such as who is the Prime Minister of Germany? Got it wrong. And that's Gemini, that's Google, that's changed on all the stuff that Google does. 42% across all those platforms had serious errors. And we see a bunch of the rising generation coming in, going to them for their news sources. So almost half of the results are just bad. And then the rest, it's like 82% that have some significant errors. That's AI. The singularity is nowhere close. But we need to be careful. But they're great tools, but we've got to be careful that we have judgment applied to them. And too many people do not understand that. They think that because it's an AI, it works. So in geotechnical engineering, we do a lot of analysis. That's the heart of what we do. We look at the earth and we make judgments based upon the data, and as we analyze it. And it's everything from sitting down doing, so that's an AI generated picture, just try to throw something there. Show me an engineer that is doing hand calculations with paper and pencil. That's what the AI thinks. But they allow us in analysis for us to be able to evaluate the responses of the system when we subject it to some type of stress or change from the current conditions. You know, there's all sorts of different tools. I'm going to talk mostly today about slope stability analysis, which is generally limit equilibrium numerical analysis. Finite element. The picture on the right is kind of illustrative of how sometimes I feel. I have these very, very high-end computer programs, and I'm dealing with a coal oil lamp. This is not AI generated. This was, we had in summer of 2020, we had what's called the derecho that came through eastern Iowa, 140 mile an hour sustained winds for an hour, inland hurricane, wiped out cell towers and everything. Took 4 days to get data, but my boss still wanted me to work. I had data before I had power. So just me working by coal lamp. So analytical tools, we are using models to analyze the site. So limited equilibrium, it is simply looking at the driving forces and the resisting forces, and the ratio of the resisting forces, the driving forces, your factor of safety. It is not a material print. It's not a fundamental material property. It is simply a ratio. The limited equilibrium models make some pretty gross assumptions, but they work well. And we see them applied well in practice. They're proven and they're true. True is not the right word. They're proven out to work well within what we know. The big part of the problem with limited equilibrium is that it doesn't account for deformation. It's a simplification of how the process works. Finite element, more complex, does consider deformation, but they're all based upon a constitutive model that's based on a set of data, which also makes them empirical. So we have to make sure that we're using the right constitutive models and training up the generation to come so that they look at that before they apply the software. Because models, and we use models all the time, not just with us, but we hear about climate models and economic models, and all these different models are basically simplification of very complex systems. And we use the models, you guys know, to evaluate the response of the system to changes in inputs. But they really need to be calibrated against what do we as the profession understand is going on. The incorrect models lead to wrong conclusions. This is another an illustration of how AI can be used. Copilot, put those slides in and give you a picture on it. So this is, I'm going to spend a little time on this because this is kind of the basis for the cases review I'm going to be talking about. Accuracy, precision, reliability, and validity. How many of you are shooters? This is reminiscent of sighting in a rifle. The 4 targets, and there's different groupings. So the one on the left is very precise, getting it close to the same point every single time we pull the triggers. However, the sights are wrong, so it's very inaccurate. So high precision, poor accuracy. The second one is if you took the loci of all those points, it's on the bullseye, but it's all over the place. So it's accurate because the average is in the center, but it's not precise. And so getting the same answer over and over, it rarely happens. The third one is just bad. All over the place, not close to anything. But where we want to be, of course, is the far right one. High precision, high accuracy. We're getting the same results over and over and over again, and those results are accurate. The challenge with geotechnical modeling, with some mentioning coefficient of variation in the previous one, is that earth materials are highly variable. We know that. It's an inherently heterogeneous environment we're dealing with. We have limited data. We talked about the 6-inch holes every 150 to 300 feet. And the empirical method itself that we tend to use, they also have high variability. So we use highly spaced data, and then we put it into an empirical model to get an answer, and then we put that into another model that has variability in it. And so the implications modeling accuracy are pretty obvious. Now, this is a table down here. Again, it's hard to see from the back, but the unit weight for clay and sand, coefficient variability is pretty small. We can get that pretty well. We can put a Shelby tube in there. We can do a moisture density, and we can feel pretty good about it. That's not going to vary all over the place. But when we get into friction angles, for sand, it's pretty well known. When we get into clay, the coefficient of variation is huge. Same with just running a PI on a single sample of soil. We can have wide variability on those test results. Unconfined compression tests. Now, I'm going to step out of my presentation just a little bit. Unconfined compression tests I've seen used by particularly developing engineers incorrectly, particularly utilizing that data in soils with plasticity that are unsaturated, and using those with a high negative pore pressure results in a high unconfined compression test, and then them not looking at the percent saturation and penalizing their results of the unconfined compression test accordingly. It's been something that has been worrisome because it seems like coming out of school they didn't get taught. They just said this is the test. Here's the results. Didn't get taught well that you got to look at the percent saturation in there. That they're only really the true result is if they're 100% saturated. We don't generally deal with that very much. So Ralph Peck, wise sage of our profession. In the engineering for such works as large foundations, tunnels, cuts, earth dams, a vast amount of effort and labor goes into securing only roughly approximate values for the physical constants that appear in equations. Many variables remain unknown. Therefore, the results of the computations are not more than working hypotheses subject to confirmation or modification during construction. The observational method. This is from his seminal work talk in 1969. So, need for engineering judgment. Human expertise is critical for interpretation. test the results of the AI outputs and analytical tools against the observed natural world, and distinguish between correct and realistic results. So how can we do that? And this is a methodology which a lot of times when there's a methodology or terminology, but it's usually on universal principles that everybody who does it knows, but they like to somebody likes to put a name on it. And so I call this the conceptual site model. And this is the working model from which sites are evaluated. It is the known site information is gathered, synthesized, and continually updated as more data is obtained. It's integration of diverse data sets. All of our geotechnical projects exist within a context of an overall project, overall site, and there's demographics, there's political, there's hydrologic, there's every sort of other variable that goes in and affects the final decision that we make as geotechnical engineers. And so the conceptual site model, in my mind, needs to consider those constraints and those boundaries. It only creates a snapshot of the site in a specific time, but it gives us something to work with. The conceptual site model we should be thinking about how did the site get to be how it is, from previous site uses, the geomorphology, those things go into it. And so with that, we can use the site model to test, to potentially predict what might occur. And it's not really a specific tool. There's not a conceptual site model. Here's my software to do that. It's a process to create a documented understanding of the site. We've always asking the question, what does the site tell us? Not what does the analytical model tell us, what does the site tell us? So it allows us to manage risk at the end of it, to mitigate uncertainty. We, of course, as mentioned before, deal with the natural environment, with the earth, with geology, which is inherently variable. Our job as geotechnical engineers is to understand that, mitigate that, and communicate that to the project, our partners in the projects, to make sure we can build something at the end of the day. But to mitigate the uncertainty, that's our job. So to develop the CSM, basically integrate the desktop and field data to create a conceptual site model. And ask yourselves, what is the science? What do I know from measured data? And then we are geotechnical engineers. What is the art? What's our creativity say? What do we interpret it to be? What does our intuition and experience tell us? Now, the belly rub, that's where the 4 of those 14 different options come from. But really, it comes down, there's sometimes when we as experienced professionals, we just have to make a judgment based on limited data. And the challenge with developing professionals is they have not yet had that level of experience. And if they go and ask ChatGPT, then they're being put in a situation to use bad information or incomplete information without judgment. And so the conceptual site model helps us to teach them to think critically, to put together the data, to ask the questions of why. What is the significance of this data that I'm collecting? How is the data interdependent? Do I understand how the site got to be that way? Do I understand the constraints within my project that I'm working on that's constraining the sites? And most importantly, can I explain this to another person? Now, I could explain it to another geohead in one way versus explaining it to a layperson in another, but can I explain that? And identify the areas of continued risk and data gaps. So it becomes the basis for analysis. What the geoprofessional understands based on their time to research, digest the data, and develop the understand the site. That creates a hypothesis of the materials and mechanisms that fail at the site prior to creating an analytical model. Before opening up slide or slope W or Plaxis or anything, just before that, do I have enough understanding of the site so that I can tell the software what's happening there, and then I can test it, my hypotheses in the software. And then as I run the software, does the model match what I understand has happened out in the field. If not, am I wrong, or is the analytical model wrong? Dollars to donuts, the analytical model. If the analytical model is telling me the site is failing, I'm looking at it and I'm looking at it and it's not failing, then my model is not right. Something that I put together does not represent the work. So my job is to calibrate that analytical model to be observed and measured. So back to this, I'm going to talk to you a couple of case histories. The first one illustrates how precise analytical results result in a mathematically correct model, but inaccurate, but provides inaccurate answers when the incorrect analytical methods are used. So we're working in the far left one today. So this is a failure up in Oklahoma. The project had previously failed and was repaired using a reinforced soil slope. So that's the original failure on the left. Soon after they topped off the last lift of asphalt, it failed again. So why? What happened? So we were called in to try to figure out what to do to fix it. And so the lead engineer that we had assigned to it was a less experienced engineer. It was kind of his first project that he was working on as the leader. So we taught him right. He pulled together a really good, solid conceptual site model. He took aerial photos and geologic maps and the borings and the plans and what they built out there and the inspection results from the construction of the RSSS, the site recon photos and videos that we did, and from that he created his analytical model. And so he based his subsurface conditions and soil properties on what he identified in the conceptual site model, and he hypothesized the global failure of the embankment soil. And just to note, the original RSS design used circular surfaces to analyze the failure and do the design fails. So here's an aerial photo showing where the moorings were along the scarp. So there's one of the toe, decent information that we were provided. Two in and around the failure, two outside the failure, one down at the toe. And from that, this engineer identified this residual clay layer at the top of the shale. And top of the embankment, this is top of the embankment, toe of the embankment. So he said, looks like there's a sloping residual clay failure. Makes sense. So we got in, and this is looked at what the residual friction angles were based on the information for the plasticity of the soil. We used lower bound friction angle for that residual clay, since that's probably contributing to it. So he ran his analysis, and he got factor safety 1.5. He's like, wait a second. So he's got in here, he's got his he's got this sandy clay, residual clay layer. He used a P angle of 10 degrees and 0 C. And that's this pink layer right there. He had his water on above that. And his model looked decent based on out there, but that's factor safety 1.5. Did that match what was observed in the field? No. So he said, well, maybe my estimates of soil properties were incorrect. So he revised and reran, and he got a failure that was similar to observed field conditions. So he had this still has a 10-degree layer there, but he really penalized this embankment fill, and he had to get it down to 16 degrees with 0 C for compacted inspect embankment material to make it fail behind the reinforced soil. So then he started going on with his repair analysis, and then he brought me in. He says, this doesn't feel right. I can't get it to work. And so we looked at it, and he said, okay. I mentioned there we had to redo his original friction angles weren't very aggressive. Down to 16 wasn't reasonable. So we sat down together and said, what was missed? His conceptual site model, I have no issues with what he put together. His original soil properties were fine. But I said, well, why are you using circular failure surfaces? Use non-circular. Just use a slide, which what we're using, use the cuckoo search, let the program look for the worst. Boom, factor safety of 1. Using those best estimate soil properties. Nothing had changed between the 1.5 and 1.0 except for the method that he used. Now, did the analytical program tell him, hey, you probably should be using the non-circular surfaces? No, it gave him an answer. In fact, it gave him the same answer that the original designer for the RSS got, that depth rock reinforced soil slope worked. Remember I mentioned before that they used circular surfaces on their original analysis. They identified that sloping shale layer as well. So it was not a matter of the software giving incorrect results. It was very precise, over and over and over again, same one, but it was inaccurate because the wrong surfaces were chosen by the designer who used the software. So from that, we developed, we had an analytical model that was calibrated to the field conditions, and now we could use that to make the remedial solution. And what I ended up doing was unloading the slope, taking most of the material off, flopping it down to the bottom of the slope as a buttress, and then using anchors to hold it in place. But that, we got back to the factor safety 1.5. And that's been 7 years since we did that one, and it's performing very well. So, number 1, always do a senior review. Never read anything else without that. And it illustrates how these analytical tools will always give an answer. Doesn't mean it's right. So we had a good CSM, good conceptual site model, to make sure that we were able to, and we were able to figure out what's going on in the analytical model, but we have to use the appropriate searches. And if an engineer hasn't been taught that or didn't realize that, that's our job as the senior people to catch that. But if we didn't catch it, obviously the previous engineering firm didn't catch it. And so there's improvement that we need in our industry. But because the models gave an answer, doesn't mean it's right. So the second case history I want to share with you today is how precise analytical results can still result in failure when the site conditions are not understood correctly. So this is an Iowa project. Iowa was glaciated multiple times, and the last glaciation that came down is what's called the Des Moines Lobe, and the ice came off of that 12,000 years ago. So it's very, very young geology. And that's key for understanding why this failure occurred. So the setting was there's a hospital right here, and they wanted more parking. And so they needed to level things out. And as part of it, they cut. And then other part, they kicked out and built the extra width on with a reinforced soil slope between 1:1 and 1.5:1 horizontal and vertical slope. Good application of RSS. They need to minimize the toe, keep it in the boundary of the property. But this, we'll see why in this case we had we had reliable results, but it failed. So this is the site setting. Here's where the slope is. This is the hospital. This is the Des Moines River. And Des Moines River is the largest river in the Des Moines Lobe. And it's a remnant river from the glaciation. But as you can see here in the topo, it is very flat uplands and then steeply incised developing drainage ways. These are not at equilibrium. We are continuing to get down one of those very V-shaped, sinuous on the outside of the bend, steep and undercut, and on the other side, failures. And the failures move the creek back and forth until that creek will widen itself out, become a nice established channel, but that doesn't happen in just 12,000 years. It takes a lot longer than that. So this is where the section at the location of the failure. They had existing grade here that cut out here. They built the 1:1 on the slope right here. And here's the section. But what's happening down here? So if I modeled as they did, this section, what's happening outside of this section? Are we looking at the big picture and the full impacts of the site? So what happened? Surprise, surprise, was a failure. The first failure occurred in 2008. You can kind of see that some of the geotextile in here and here. In 2019, it continued to progress. They had to close that part of the parking area and said, we need to fix this. Just more examples of what the failure to set down at the scarp here. This is where that scarp failure was here. Can't kind of see it in this, but there's creek over here. So what happened was the RSS was fine if it was in a static location with nothing else happening to it, but it wasn't. It was a very dynamic situation. There was a creek down here. You can see the very steeply incised creek. Creeks don't like straight lines. Water doesn't flow in straight lines. Water likes to be sinuous. And it happens to be that they built it on the outside of a bend in the creek. Because the geology of the site was so young yet, it's still trying to come to equilibrium. And we superimposed infrastructure on top of a site that wasn't yet in equilibrium. And we interpreted that the failure was due to a loss of toe support. So the original repair was limited equilibrium methods, very standard, was a good RSS design. They had it well documented. We went through and we confirmed their calculated results, matched the initial designs. So then we did our post-failure analysis to calibrate the soil properties. And then we identified the problem with their model was design was that they did not take into consideration the geologic setting of their project. So back analysis, here's the RSS is just perched on the top. Service conditions met the factor safety 1.3. However, with a saturated forest slope, factor safety dropped below 1. And as a result, they lost all this out here. This was unstable and had a factor safety barely above 1, which when it rained, more toe was lost at the bottom. That would continue to go down, continuing to progress until it came back to an angle of repose, probably right around 2 to 1. So we use that calibrated an analytical model to develop the repair, and our repair accounted for future creek erosion and additional loss of toe. So we basically, instead of just repairing that RSS, we took the slope and put a reinforced shotcrete and soil nail wall much deeper. Used hollow bar, soil nails, and shotcretes, and we checked stability at normal everyday conditions. We checked at service conditions. As the service conditions, we also checked extreme. Now, we talked earlier about the most limited slope stability. We look at factors of safety ASD design, which is a single number. I personally still use ASD analysis, but I use the service limit cases from LRFD to check it. So normal service, extreme, and that's earthquake or flood, high precipitation events, rapid drawdown. Look at all of those different conditions that slope might encounter during its lifespan. So our repair, we took it back to that 1.3 because it's a parking lot. There's not a structure. We felt 1.3 was appropriate. And we looked at it, both the service limit, and then we saturated that toe, and we still had the factor of safety that we needed. So here's some pictures of construction. Here's the hollow bar soil nails. How many are familiar with hollow bar soil nails? I know soil nails used a lot here in Texas. But basically, instead of doing an open hole and putting a bar down with a centralizer, the reinforcing steel is your drill stem. And so you drill in the ground, pump grout through the middle of the bar, flushes the cuttings out, and then once you reach depth, you pump grout so that all the cuttings are out, and get clean grout back, and you leave the bar in place. So each one, so there's no, it's a single step process rather than two-step process like traditional solid bar soil nails. And the FHWA manual recognizes both as legitimate strands to be used in soil nail walls now. Anyway, so here's here's a lift is done, getting ready to drill the next lift in there. See the drainage strips that are continuous, that are flipped over the top so they can continue to move those down. And this is the completed construction. It's not very pretty, but there's no view shed over here. This is a drone taking the picture. It's just woods over here. They didn't want sculpted shotcrete. They didn't want a trowel finish. They just said gun finish is fine. We just want it to be up and moving. And you can see cars are now parked atop. So in summary for this case history, again, analytical modeling can produce results that are precise, that can be reproduced over and over. The original designer for the RSS used a stable 6 engine, slope stability software, and we used slide, and we got the same answer using the same input properties. The problem was it didn't match the site. It didn't take into consideration the geology and the conditions that slope was going to be exposed to. It just looked at the stability of the reinforced soil slope.
Well, how do you control the erosion at the top if the creek is still active?
So like we just said that it's going to come out. We just checked it against it with more and more total loss. So what we did was we doubled the height of the walls so that the force slope was flat, much flat. And then we allowed for loss over time. And then
So you didn't do any erosion control. It's just merely allowing it to take place and taking a higher demand into account in the
Yeah.
stabilization.
exactly. So the endpoint geology matters. You're hiring a young geotechnical engineer, ask them what they thought of their geology for engineers course. If they didn't like it, probably ought not to have them be a practicing geotechnical. So, in conclusion, human judgment is irreplaceable. The tools that we have to use to aid our judgment are getting better and better and better. But we have to understand the limitations of those tools, both the ones we control everything in, the analytical model, or the analytical tools. But even with them, if you're running are you going to run a Spencer analysis that meets both moment and force equilibrium, or are you going to run a Bishop's analysis because it's quick and you can do a hand calc check against it? Are you going to use with it like Plaxis? What is the constitutive model that you're using? Strain softening, strain hardening. You still got to pick because those models have assumptions built into them. We cannot turn the judgment over to the software, and we cannot turn it over to AI. Precision does not guarantee accuracy. And a tool to help with that is the conceptual site model, because it helps us validate the models that we have created and make sure that those models align with reality and what we anticipate it to be. Thank you. Any questions, comments?
It looks easy to get engineering judgment. So what do you recommend one does to form that judgment, other than being in the courtroom?
Yes. Well, experience, varied experience. Like for me, I'll just give as a young engineer, I had a site where we had a potential liquefaction problem. There's old creek beds that had been buried during the construction of I-405 outside of Denton, Washington. And we were putting a new ramp across it, and we were running analysis, and I had my model set up, and my gut was this should be failing, but it wasn't. It wasn't failing. I changed all sorts of stuff, and it just wasn't failing. It says, this doesn't feel right. So I turned it into my senior reviewer, and he looked at it, and he knew immediately. He said, Roch, you're using circular failure states. Because again, it wasn't catching this liquefiable layer, even using huge radiuses. It wasn't catching it. And then once he fixed me and I fixed the model, it failed. I knew enough at that point to have a sense that it would fail just based upon what the configuration was, but I didn't have enough experience to have had that mistake be corrected by a senior engineer from that. Okay, so it's basic experience. Putting them out on the rig, getting the dirt underneath their fingernails. Didn't see if it's silk or clay by rubbing it on their teeth. Now that as much construction oversight experience as we can get. One of the things I was blessed in my career was that about 3 years out of school, my family and I, we moved to Alaska. And that's where I did my first design build experience project. It was a big one at the time, $45 million for an interchange up north of Anchorage in the middle of a swamp. And it was just really cool. And I spent a lot of time out there with construction, seeing how variable they were digging for footing, seeing how the soil changed across the whole thing. And we had one boring that represented one area. And how did I account for that? And what changes that we made? So it's as varied an experience as possible. I know it's easy sometimes to have a young engineer be out slunking concrete for 6 months. A couple of weeks of that will teach them a lot. A couple of months will suck them dry. So find ways to get them varied experiences so that they can just be able to have enough real world vision so their mind's calibrated with their empirical models based on real world data and not just sitting on the desk learning software. It just takes time. I mean, this profession, it takes time. I found the best acceleration for development is intentional development, intentional exposure to different things. That it may be the easy button to put them on this, but it'll accelerate their stuff by years by putting over on this one. And just making the sacrifices for the investment in the company into the next generation. But it has to be intentional.
Well, going to conferences, listening to case histories are all ways to broaden one's appreciation for the variabilities.
Absolutely.
Method.
Yeah, and that's the other thing. It's great to see the experienced professionals here. But how many of you have young developing professionals that aren't here because they are really busy doing the day-to-day work? And that's great. But being able to be recognized as part of a profession, and that we as a profession have an obligation to help raise the bar.
So you mentioned the non-circular clear surface methods. Is there the methods option available in the software?
Yes.
What kind of specific approach? Is it kind of predefined path for children? So it cannot be too random.
Yeah, there are multiple versions. Some of it's like PC Sable 6, the early engines. You have to define a box where the surfaces would enter this. And so based on like that model of the sloping shale surface, I would put a box along that. Because I know based on my judgment, or I believe based on my judgment, that that's where the critical finish is. Slope W and slide particularly have built-in mechanisms for doing random non-circular surface generation. So they're usually hundreds of thousands of surfaces within a short period of time. But you still need to be carefully used because some of these algorithms will find a low spot and just keep working on it and miss another spot that actually might be lower. It's an apparent low factor safety versus a low building. So it's a matter of one different platforms and stuff. But now it's much easier. When the danger is, it's much easier to have the software do all the searching for you versus in the old days, which you had to apply some judgment to where the search.
Well, the same on the highway, the first case study we presented, if you were the first designer to design a reinforced slope, what changes would you make, to avoid the failure?
What I would have done was identified that and do non-circular surfaces. I would put a key in, a toe key. So cut it out and put a large toe key at the bottom to cut off those potential failures and reinforce that, and then build the rest of the reinforced slope.
So that's to be deeper in the beginning.
Yeah, okay. Carefully.
Can read up.
It's saying it's construction because it wants to become benefit on me, but yes, in that way, would have to be the key would be cut off that. I don't think I think a structural solution like a stone nail might have worked, but, not without a buttress. The key for that fix was the buttress at the top.
How did the butters not form a dam to create, allow the water surface to increase and create an unstable condition? Was drainage added?
That one, yes, there was horizontal drainage, so.
Okay.
But yeah, it's the unintended consequences. We have a project right now that we're dealing with where there is very moisture sensitive soil and they had it open for the excavation, open for a footing. It rained, got the bottom all mucky, dug it, and so the contractor asked the field engineers on site, hey, what do we do about this? He's like, dig out 3 feet and put 57 stone. Yeah. And because it had been successful before, except right after they put the stone in, before they put the foundation and buried it mid 3-inch rain. So all that water down into that 57 stone and then softened the bottom below that. So when things were loaded, they settled. So now it's like, okay, what do we do about this? Because should we, as the geotechnical engineer, have known that not that we're putting something in there that if it's not protected against water, we're creating a bath? The answer is yes. And at least what the lawyers probably say. But it's a, what is the unintended consequences of the decisions that we make? That's where we have to look at things in context, not just what does the one boring say, or what is this one footing? What am I doing this one footing? But look, if I do this, then what? All right, thank you guys very much.